So hope my screen is visible.
Yes, ma'am. Yes, ma'am.
Yes, sir. Thank you, sir. So, okay, once again, good morning, everyone. So today I'll be presenting an in-depth overview of the truly revolutionary material in the field of civil engineering, which is nothing but this ultra high performance concrete, which is otherwise called as UHPC. So, we'll see the detailed journey of exploring what is UHPC, the science behind its incredible properties, how it is made, and its real-world applications, and what are the challenges it faced, and the exciting future trends that promise to redefine your infrastructure. And also, we'll see how UHPC got an incremental improvement and the shift in normal conventional concrete to this UHPC, which is nothing but this ultra high performance concrete. And also, we need to talk about the UHPC because of this infrastructure crisis which we are now facing. And also, we'll try to find out a solution for this durable, sustainable, and the resilient structures. So this is my content for the presentation. So to guide our discussion, we'll cover with the following key areas. I'll begin with the introduction, where I'll define the UHPC, which is once again UHPC is nothing but ultra high performance concrete. So I understand the need for such an advanced material. Then we'll look into the characteristics and the materials that gives this UHPC its superpower. And then we'll discuss the mixed proportion, production, and the curing method, and how it is important. Following that, we'll look into the practical applications and constructions with a focus on case studies, particularly in bridges. Then we'll address the sustainability aspects and the challenges impending in the widespread uses. Finally, we'll look into the future trends and the research directions, where we'll explore the integration of AI, 3D printings, and the bio-based materials. So finally, we'll conclude with the and the last slide will be your reference slide. Coming to the introduction of UHPC, which is nothing but the ultra high performance concrete. So as we all know, the conventional concrete, which is made up of fine aggregate, in a simple term, if you want to explain what is this ultra high performance concrete. In the conventional concrete, we use the cement, fine aggregate, coarse aggregate, and water together, combined together, we make it as a concrete. Whereas in case of a ultra high performance concrete, the coarse aggregate part is eliminated, so which is mainly cementitious composite material, which is characterized by exceptionally high strength, durability, and ductility compared to that of a conventional concrete. So it is a material which is mainly made up of cement, the supplementary cementing materials, and the admixtures, and the fine aggregates. So here the coarse aggregate is eliminated to produce a uniform bulk mass. So in order to improve the ductility, we are going to use it. Normally in practice, the steel fibers are added to improve the ductility part of your UHPC. So, UHPC is a class of advanced cementitious composite characterized by exceptionally high strength, durability, and ductility compared to that of a conventional and even high performance concrete. So it is not just improved concrete. So it is a fundamentally different material with a tailor made microstructure. So coming to the composition of this UHPC, so we can break down its composition into three categories, or the compressive strength, the post-cracking tensile strength, durability, and what are the unique properties of this UHPC. So coming to the composition, it is a cementitious material. The UHPC is carefully engineered composite material So its formulation involves optimized gradation of granular constituents, meeting the particle size, are selected to pack together with extreme density. So here the particle packing density is, which is a main important parameter to be considered in the design of a UHPC. So it has a very low water cement ratio compared to that of normal conventional concretes, where it is 0.35 to 0.4 and 0.5. Whereas in case of this ultra high performance concrete, the water cement ratio normally adopted is less than 0.25. So you can assume the comparison between your conventional concrete and your ultra high performance concrete. So although it is a water cement ratio is 0.25, how this workability we are going to achieve? So that is the main thing which we have to concentrate on, this ultra high performance concrete. Uh, so this low water cement ratio of less than 0.25, which it will minimizes the capillary pores, that weakens the that is a weakened part, that is a weakens in the ordinary concretes. So finally, it induces a high percentage of discontinuous internal fiber reinforcement. It may be of steel or polymer fibers, which provides a signature ductility. So coming to the compressive strength, we'll talk in numbers, since it is compressive strength is related to the numbers. We'll talk in numbers. The compressive strength of UHPC is extraordinary. So the values started with achieving a value of 120 megapascal, and now it has reached up to 150 megapascal, and still furthermore it has reached up to 200 megapascal. Typically it is greater than 137 megapascal. So coming to your normal conventional concrete, the range of strength ranges from 20 megapascal to 40 megapascal. So you can see the difference between the normal conventional concrete and the strength difference between the normal conventional concrete and the UHPC, which is nothing but the ultra high performance concrete. So so if you see, it is even more impressive to see the behavior after cracking. So while normal concrete fails by brittle, this UHPC, that is ultra high performance concrete, maintains a good post-cracking tensile strength, sustained above 5.2 megapascal. So it is those fibers, the steel fibers or the fibers which you are adding, bridges the micro cracks. So this is the fundamental shift in concrete behavior compared to your normal conventional concrete to your ultra high performance concrete. Next thing is your next important aspect is your durability. So the durability, it is another parameter. The ultra high performance concrete has a discontinuous pore structures, so that act as a barrier, significantly reducing the ingress of water, chloride ions, and other harmful agents. So thereby drastically enhancing its life longevity. So to summarize, it is a UHPC. UHPC is a no coarse aggregate concrete with a very low water cement ratio, less than 0.05, and the ductility is improved by the means of steel fibers. And also, although the water cement ratio is less than 0.25, it is said to be a self-consolidating or a self-compacting concrete, and also it has excellent durability. So next, why this? Although there are a lot of concrete now in practice, why and what is the purpose of, or what is the need for this UHPC? So UHPC typically utilizes, as we said, aggregate, low water cement ratio, fibers, and self-consolidating and excellent durability. So why we need this? Why we need such a material with low water cement ratio, and fibers are added, and you have to use accelerators or water workability improving agents, and why it is so much needed, and what is the need for this UHPC? So the modern construction materials demands that are durable, corrosion resistant, and sustainable. So the conventional concrete often struggles in harsh environment like marine or the regions that uses de-icing salts. So it's which leads to the cracking, corrosion of rebar, and high maintenance cost. So this UHPC uh, provides an directly addresses the limitations of inadequate toughness, poor crack resistance, and the frequent repairs needed in case of use of this conventional concrete. So furthermore, the architectural trends, the shift in the architectural need. So more elegant designs are required compared to that of a normal concrete. So you can achieve a slender, elegant designs with high compressive and the flexural strength in case of this UHPC. So there is a material shifting from this Roman period to the advanced composite materials. So one of this is this UHPC. So although we see if you see the performance of UHP, if you see the benefits of UHPC, so it is it reduces the material usage since we are eliminating the coarse aggregate content, and we can develop a lighter weight structures with a longer span, and it enhances the sustainability and the life cycle performances. So coming to the history of concrete, so first it is an hybrid material which is made up of which is combines the properties of three different types of concrete. The one is your self-consolidating concrete. Next one is your high performance concrete, and the other one is your fiber reinforced concrete. So it is the UHPC is a easy flowing self-consolidating nature of SPCE. So it has a property of self-consolidating nature of SCC. So it fills most complex forms effortlessly. The second one is it possesses the superior strength and the durability of high performance concrete. Next one is the fiber reinforced concrete. So it increases, it gains the increased ductility and the post cracking strength from the fiber reinforced or the fibers which we add to produce this UHPC. So by integrating these three powerful characteristics, we can get a single advanced material known as self-consolidating ultra high performance fiber reinforced concrete, which is otherwise called as PFRC, which is otherwise nothing but your UHPC. So why this UHPC? So new materials was always redefined what is possible in the constructions. So this UHPC represents one of these fundamental shifts, much like this introduction of the steel, so when in olden days we generated or we built structures using the only concrete. Later, when the steel came, so it's another next evolution of your concrete. So the UHPC presents one of these fundamental shifts, introducing much like the introduction of your steel. So the creation of the trusses and the suspension bridges. So next one, the UHPC was first developed, or it was first originated or developed by the US Army Corps of Engineers in late 1980s, and it was commercially launched in the year 2000. So if you see, it is availability is prompted by the Federal Highway Administration to initiate the major investigation for highway uses, so which subsequently spurred the wide university researches. So in the first bridge in North America was a pedestrian bridge in Canada, which was built in the year 1997. And also, if you see the globally, so 34 research projects across multiple institutes were uh, initiated, and it is in ongoing, and it is a lot of projects are undergoing, and it is available, and it is economically feasible. So coming to the performance criteria, as we already discussed. So the UHPC has a high compressive strength, which is 10 times that of a traditional concrete. So the compressive strength is the ability of the material to resist your bending under the loads. So normally, the normal concrete used in the bridges is a high compressive strength, uh, ranges from 30 megapascal to 20 megapascal to 50 megapascal. So whereas UHPC uses has a strength range from 150 megapascal to 250 megapascal. So coming to the workability, it has a self-compacting mix. It can be developed using a self-compacting mix by achieving optimum particle size and using the high range of. So this workability is achieved by using a high range of super plasticizer. Next one is your durability. So while UHPC strength is impressive, so its durability is further exceeds expectations. So the durability is measured by how the material performs under extreme condition, freeze-thaw resistance, chloride resistance, and the abrasion resistance, which are all the part of your the durability aspects. So this UHPC properties is similar to a hard rock, which has a resistant to chemical, chloride, fire resistance, and it has a zero maintenance. Next one is your affordability. So although we say UHPC has high strength, its thinner sections can be made, but compared to that of a cost of this normal conventional concrete to the UHPC, the cost of UHPC cost, if you see, the cost of conventional concrete is found to be somewhat around 14,000 per cubic meter, whereas uh, the cost of your UHPC is ranges from 2 lakhs to 2 lakhs 15,000 per cubic meter. So you can see the cost comparison of this normal conventional concrete to your UHPC. So the next part of my presentation is just a second. So the second part of my presentation is the science behind the making of UHPC, which comprises the material composition, the mix design principle, the production process, curing methods, material properties, testing methods, and the safety and the handling. So if you see the materials which are mainly used for the production of UHPC is the main basic materials are the powders, superplasticizers, and the organic fibers. So the general formulation of UHPC consists of high binder content, including Portland cement, and the supplementary cementitious material like silica fume and quartz floor. So the coarse aggregate is removed from this UHPC, which we have already discussed, to avoid the formulation of high voids and to create a densified interfacial transition zone around the aggregates. So this elimination of this coarse aggregate will eliminate the weakest region within the matrix. Next, the coarse aggregate is replaced with this. So now we have eliminated this coarse aggregates. How come the strength is achieved, and how we are going to achieve this dense packing? So this coarse aggregate is replaced by a well-graded fine sand to ensure the high packing order. So this UHPC mix design is incorporated with the two different types of chemical admixtures, namely high range of water reducing admixtures and the concrete setting accelerators. So finally, we'll get a finally the micro-sized steel fibers are incorporated to increase the mix strength and the ductility. So here you can see the proportion of the composition of the UHPC. So this is not the proportion which is normally adopted throughout. So this is one of the proportion which is adopted in in the preparation of UHPC. So here you can see the Portland cement. The amount of Portland cement is 700 kg per meter cube, and the fine sand is 1020. And the aggregate, since we have eliminated this UHPC, does not contains this coarse aggregate. The fine sand, it is 1020 kg per meter cube, and the silica fume, it is 231. Ground quartz is 211. High range of water reducing admixtures, that is 37%, 30 kg per meter cube, and 30% is your accelerated, and the steel fibers is 156 kg per meter cube, and the water added is 107. So if you see in normal conventional concrete, the water normally adopted is 185 kg per meter cube. So, but you can see the comparison of this UHPC, the amount of water added. So this is this figure represents the particle packing of this UHPC. So here you can see this, the yellow one, which is the coarse aggregate, and the smaller one is the fine aggregate, and the cement paste is represented by this blue color. Here you can see how the in case of UHPC, how the pores are tightly packed, and you can see the pores in between, and the particle packing density of a conventional concrete and the UHPC. So here you can see how the pores are evenly fully packed, and the supplementary cementing materials and the filling powders and the fibers which are added and are fully packed to form a dense matrix. So next we'll see about the detailed mixing procedure for this, how this mixing sequence of this UHPC. So I'll just quickly go through, quickly tell. So the dry powders, which is whatever we have taken, that is cement, supplementary cementing materials, and which may be a silica fume, blast furnace slag, the fine silica sand, which are dry mixed at for 2 to 3 minutes. Then with a uniform speed, so to obtain a homogeneous dry mix is achieved. Then once it is done, the liquid is added, just a second. So once our dry mix is perfectly homogeneous, we'll transform the powder into a paste. So we gradually add the large portion of the total mixing water, typically which is between 75 and 90%, along with the dosage of high range of water reducer or the super plastifier. So as we continue, so the dry powder will absolutely absorbs the moisture and the super plasticizer, turning into a thick cohesive paste. So this super plasticizer is a crucial here. So it is eventually allows this very dry, dense mixture to make it to flow like a fluid. So the step 3 is the remaining water, which may be 20 to the 10% of the remaining water, is slowly added to form a final consistency of the mixes obtained. So this final mixture, which is again mixed for 2 to 3 minutes to obtain a uniform mix. So next one is the last step is the fiber incorporation. So this is what this UHP is remarkably ductile, and the post-cracking tensile strength is obtained by mixing this fiber. So while the mixture is running, we slowly add the steel or the polymer fibers for another 3 to 4 minutes. So the steel or the polymer fibers, which uniformly distributed throughout the cementitious matrix, and the homogeneous mixtures is obtained. So this mixing of the fibers should be uniformly distributed throughout the matrix, because once the fibers are added, what happens is it will clumps together. Clumps will be formed, and the fibers will not be uniformly distributed. So the last step is the casting. So as the casting is similar to that of a normal conventional concrete, it is poured into the mold, which is already prepared, and although we say it is a the self-consolidating concrete, it is normally kept in the vibrating table and it is casted. Next one, curing. So curing, since in conventional concrete, the hydration is the main thing which will enhances the strength and the strength of the concrete. But here the water cement ratio is less than 0.2. So then, what is the hydration? What about this hydration effect? So here, this strength is achieved mainly by the means of the densely packed UHPC. So the curing is done immediately by covering an exposed surface with a plastic sheet or by using a compound, spraying a compound to prevent the moisture loss. Then the mold is kept at a room temperature of 20 to 25 degrees for 24 hours. Then after that, it is demolded, and the final curing is done at a temperature of 20 degrees or at a relative humidity of greater than 95%, or in a water tank for 28 days. So commonly, if you are using a precast element, it has to be done at a controlled temperature, to an elevated temperature of 60 to 90 degrees at an elevated temperature. The precast elements can be cured for 24 to 72 hours. And there is so the heating, as we all know, the heating provides the strength gain. So the heating drastically accelerates the strength, which enhances simultaneously the strength and the durability of the is achieved by promoting the pozzolanic reactions with the silica fume. Now let's move into the third part of your UHPC. So so now we have learned, or we have we saw the last 30 minutes. We have been seeing what is the science behind the UHPC and what is the historical background and what is UHPC. So now we will see what is the real world applications, focusing on how this revolutionary material is being used in the construction industry, and the case studies, some few case studies related to the bridge construction, and we also look into the exciting potential in architecture. So we are going to see about the application of UHPC in construction industry and the innovative projects and the innovations in the precast concrete, and we are going to see what do you mean by this architectural UHPC. So if you see the application of UHPC in construction industry, so the UHPC is primarily used in the construction of the bridges. In bridges, it is mainly used for the it is mainly used for the construction of the bridge decks, which is primarily the superstructure of the which is considered to be which is the main primary superstructure of a bridge. So here the bridge deck is the one which carries a heavy traffic load. So this UHPC, which provides to be a strength of around 200 to 250 megapascal, is primarily used in the casting of it's mainly used used in the bridge deck. Not only in the bridge deck, it is also used in the connection between your pier and the bridge deck. So due to this high cost, the UHPC is primarily restricted to very important or the projects. So the first UHPC is used in the North America in the year 1997 in the construction of the pedestrian bridge. Next one is the UHPC became available in US and from 2000. So although the evolution of UHP started in the late 80s, but the full project or the complete evolution of UHPC is the started in the year 1997, and furthermore, it is extending throughout till now. So next one is the first UHP girder bridge was first erected in Mars Hill Bridge in Iowa. So it is a, if you see the specific features of this bridge, it is a single span, a three beam cross section bridge with a span of about 33.5 meter. So if you see the applications of UHP in the construction industry, it's mainly, as I said, it is mainly used in the construction projects of production, building of bridges. So over 2,000 bridges projects in US is used in the, has used this UHPC mixes. So this application includes new bridge construction and the maintenance of the existing structures. So although we talk about the UHPC is mainly used for the construction of new structures, the another important application of UHPC is it is used to strengthen the structures, it is used to repair the structures, or it is used as an overlay of the structures. So the major contribution of UHPC in the bridge construction and the maintenance is, so the entire bridge structures is made up of UHPC elements, and it is also used as a connector, that is joining the precast element with the other component, and is also used to strengthen the existing piers, and is also, as I said, it is also used as an strengthen the bridge decks. So it is also used as an overlay on the bridge decks for the improved long life of the structure. So next one is the repair. So it is the UHPC is used for repairing these corroded steel girders. The high fatigue resistance and the enhanced durability makes it as a conventional method for this conventional make it is available for this repair system. So as you can see, this UHPC, here we are using the steel fiber, which provides a superior bonding, and it also eliminates the corrosion. Next one. So if you see the evolution of, or if you see the historical milestone in the bridge construction, so the revolution nature of UHPC, see, we must look the project that started in Sherbrooke pedestrian overpass in Canada. So this bridge is a landmark in engineering history because in 1997 it becomes the world's first bridge to use UHPC. So this bridge was built using a single massive 16-meter span, which used 6 precast post-tension steel truss elements. So this bridge was constructed using an reactive powder concrete, which was the earlier version of this UHPC, with a compressive strength ranging from 200 megapascal to 350 megapascal. So next, you have this another UHPC. We have this the joints are made up of use this UHPC with high durability and the corrosion resistance. Next one. What is the next application of UHPC in the bridge repair and the bridge repair system? So beyond our new construction, the UHPC is truly transforming how we maintain and strengthen our existing structures, which is seem to be a costlier one. So first, we'll see about the spear jacketing. So this technique involves applying a thin UHPC encasement around the existing bridge columns. Why this is so effective? If you see, it provides far superior confinement compared to that of a normal steel jacket system, and it enhances the seismic resistance. And the another one is this the application of this UHPC in the deck overlays. Normally, does to strengthen the deck, 1 to 2 inch of protective layer of existing deck is provided by the means of this UHPC. So it provides an impermeable, crack-resistant surface with increased load-carrying capacity, which provides to be a long-term solutions and the frequent, which cut down the frequent repair of this deck slabs. This UHPC is also used in the restore the corroded girders which has been which uh, constitute a major cost. So this UHPC provides a solution for this bridge end repair system, and it provides a super bond with this old concrete, and the and it provides a high fatigue resistance. So if you see the evaluation innovation in the precast system, so this production of the EHPC precast elements, which can be done in a controlled environment. And if you want to do a mass productions, we go for this precast concrete elements. Normally, the bridge deck, which is mainly just a precast, the deck slab, which is made up of precast. So this ultra high performance concrete represents a cutting edge of concrete technology, which enables the precasters to create a new product and solutions. So this UHPC provides strength, durability, and moldability. Uh, you can make any type of structure with this UHPC. So coming to this architectural UHPC, what is this architectural UHPC? So this architectural UHPC, again and again I'm telling, this UHPC is nothing but this ultra high performance concrete. So this architectural UHPC is a specialized formulation of ultra high performance concrete, engineered to combine exceptional mechanical properties with aesthetical versatility. So it enables the creation of slender, complex and sculptural elements that are both structurally sound and visually striking. So you can see this figures. You can see this structures, which is thin structures, which is aesthetically, which has an excellent aesthetic appearance, made up of this UHPC. So if you see this UHPC, the architectural UHPC, it has a similar to that of normal UHPC. It has a compressive strength ranging from 200 megapascal and the fluxural strength ranging from structural strength of 200 megapascal. So mainly since it is a thin structure, which is mainly used for the architectural purpose, the fibers are maybe made up of this polyvinyl alcohol fibers. The compressive strength ranging from that is 170 megapascal, and the fluxural strength ranging from 20 megapascals. So this UHPC provides a better solution, or it's a concrete which satisfy both the structural as well as the architectural needs. So it's more flexible. It has a good compressive strength and the fluxural properties, and it eliminates, since mostly the fibers are used as fibers are mainly used to improve the ductility. It reduces the reduction of a use of passive reinforcement, and it is highly moldable and precisely replicate. You can replicate a number of products with this UHPC. Since the limited use of steel fibers is purely architectural, and it can be adopted in hybrid projects. So the next challenges, or the next part of my presentation, will be this: what are the difficulties for using this UHPC? What are the sustainability and the green? What do you mean by sustainability and the green UHPC? What are the advanced and the smart UHPCs? What are the future directions and the global trends? So So if you see, so if you see the difficulty, or if you see uh, the hindrance in using this UHPC is, so there is a lack of specification and the codal provisions for the design of UHPC. So there is no comprehensive design procedures or the standard course for the UHPC in many countries. Still, they are working on this, formulating the codes for this design of this UHPC. So the existing guidelines in France, Japan, and Australia aims to standardize UHP behavior and the performance. So in India, we have achieved a milestone. The recent milestone uh, uh, is the steps is the use of the recent milestone is the IRC SP 120 is the recent publication of this uh, guideline for the use of this ultra high performance concrete in the bridges. So in United States, UHPC has been commercially available for over 2 decades, but there is no authoritative documents or the defined mixed constituents, batching, or the quality control procedures are available. And the no national design codes exist for the accurate UHPC member capacity calculations. So the current projects depends upon, so these are the things focus, the researchers has to focus for the, if for this development of this UHPC. So no foreign current projects mainly depends upon the foreign guidelines and the laboratory based test results for the validations. So next one, if you see the next hindrance in the UHPC is the so there's a significant gap in the industrial experience. That is, the contractors and the subcontractors often lacks hands-on experience with this complex multi-step batching and the specific curing regimes of this UHPC. So this unfamiliarity leads to the hesitations of adopting UHPC for the large-scale projects. So the another main drawbacks or main hindrance in using this UHPC is the cost. So which the conventional concrete, as I said, the production of conventional concrete is normally it is 14,000 to 15,000 per cubic meter. Whereas in case of a UHPC, the cost ranges from 2 lakh to 2 lakh 50,000, which seems to be a very high, and it is mainly used. It can be used for the very important projects. So this, if you see, this high cost is due to the use of this random steel fibers in large quantity, which is mainly used to improve the durability aspect, the expensive supplementary cementitious material, and the high dosage of chemical admixtures, or the setbacks, or the high cost, or the which constitute the high cost due to the cost of this UHPC. So if you see the sustainability and the green UHPC, yes. So to address both the cost and the environmental concern, the industry is aggressively pursuing greener UHPC. So the first, so it is mainly categorized into 4 policies, that is eco formulations, biofibers, circular economy, and the resource efficiency. So the eco formulations are using low carbon binders and the low carbon neural additives to slash the material's embodied carbon from the very start. So next one is the usage of this biofibers. The biofibers like hemp, sisal, and the flax can be used to improve the ductility of this, to replace this steel fibers. Next one is your circular economy. So by incorporating the recycled aggregates and the industrial byproducts, and also by turning the waste into highly valuable resources and dosing, and can reduce this, can align with the circular economy. The next one is your resource efficiency. So the resource has to be the ultimate goal is the fundamental shift in the focus towards the resource efficiency. So ensuring that every gram of the material is used for the maximum potential throughout the structure's entire life cycle. So this are the advanced. So these are the. So beyond just being strong and green, the next generation of UHPC is being intelligent and ultra silent. So the different types of smart UHPC in practice. So it's a self-sensing UHPC. We have the self-healing UHPC, thermal adaptive UHPC, multifunctional UHPC, AI integrated UHP systems, nano-engineered energy harvesting UHPC, bio-inspired UHPC, quantum, and the programmable UHPC. Next one, we have this ultra-ductile and the bio-based UHPC. So this has an it has an ultra high ductility, which refers to the ability to undergo significant tensile deformations and the strain hardening after the first cracks. The sustainability, it's a reduction in the environmental footprint of the material. Next one is the bio-based UHPC development. So the usage of the bio-derived additives on the bio-based fibers can reduce the usage of this steel fibers for the production of UHPC. So the partial replacement of the cement with the bio pozzolanas or the fillers, that is rice husk, GGBS or the biochars, can be an additive to reduce the usage of the cement in the production of the UHPC. Next one, the bio-based fibers such as fibers which are derived from the bamboo, flax, hemp, and the sisal can be used to replace the steel fibers. So the other thing is this: you can use this recycled aggregate for the production of this UHPC. So if you see this, next one is the UHPC in the structural health monitoring. So the self-sensing so the self-sensing ultra UHPC typically consists of dense cement matrix embedded with functional fillers. So the steel fibers are commonly used to form an interconnected conductivity network, while nanocarbon materials like materials are used to which are piezo-resistive, which has a piezo-resistive effects, can be used as an replacement of this steel fibers. So you can just sense the life of the structure by using this piezo electrical resistivity or the piezo-resistive fibers. By the use of this piezoelectric or the resistive fibers can be used to sense the lifetime of the structure. So the usage of this steel fibers can be cut down, and the carbon nanotubes and the carbon nanofibrils and the nanographic platelets can be used for the as a fillers, and the usage of this fibers can enable the real-time structural health monitoring system for the civil infrastructure. So next part is the integration of AI for the predicting the performance of this so the next one is the integration of AI for the predicting performance of this ultra high performance concrete. The true power of this self-sensing UHPC is unlocked when we pair it with the artificial intelligence. So this integration creates a powerful system for predictive modeling. So these AI enables us to accurately forecast the material mechanical properties, durability, and even its own sensing performances. So this is considered to be a game changer, supporting the advanced structural health monitoring system and allowing the engineers to optimize the mix design. So how can be achieved? So it can be achieved only through this AI approaches. Specifically, the machine learning and the hybrid algorithms can be used to uh, optimize the design, and you can see the real time sensor outputs. So the results in this AI can accurately predict the properties like compressive strength, flowability, and the long-term durability. So this we move from the reactive maintenance to the truly predictive and the resilient infrastructure management. So to model this, if you the key machine learning techniques to model this complex behavior of UHPC, researchers have used this powerful machine learning algorithms and techniques like gradient boosting, decision trees, support machines, and the neural networks to develop this UHPC design procedures. So you can also use this expandable AI tools such as SHAP. Not much. I cannot explain not much on this machine learning techniques. So these are the techniques which are commonly adopted for the production of this UHPC, and also the advanced methods like hybrid models combining multiple approaches, real-time data fusion techniques can be used for this uh, data driven can be used for the driving data from driving data and the designing of this UHPC. Next, we are going to see about the properties of this UHPC in the elevator temperature. So the fire poses a major threat to the safety and the structural integrity of this reinforced concrete. So this ISO 834 is internationally recognized standards providing a temperature fire curves for the testing the structural element. So several regional standards are used to assess the thermal performance of this RC element. So this UHPC provides a good resistance to fire at an elevated temperatures. So next comes in the evolution of this UHPC, the next one is the 3D printable UHPC. So here you can see the different types of the printing system which are mainly used for the printing this UHPC. So the robots and the pumping systems and the extruder systems are these are the components which are used in the printing of this UHPC. So if you see this printing system, so this has an three-axis gantry robot. So the core frame of the printer is an A gantry. It's a structure which moves along this. So this is a robot which moves along this direction to print the system. So it has a three-axis system, and here you have this piston in which it is a critical component that defines a printing specialty. So next one is a rectangular nozzle. So you can change this nozzle shape, whatever may be the shape you require. You can just change the shape and print the system. So if you see this, the printing procedure, so the speed is 6.5 millimeters per second, and the extrusion rate. So this indicates the volume of printing the filaments being pushed through the nozzle. So the time taken for this each totally of 3 layers will be printed. So the wait time for time between each layer is 3 minutes. So this is a picture showing how the specimens are printed and how it is cutted to the desired shape and it is cured, transferred to the controlled curing room. So next we'll see how this. So if you see the research and the future direction, so if as we push the boundaries of UHPC to intelligent self-sensing system, so although there are a lot of challenges. The challenges, first we have the challenge of this dispersion. So the incorporating the nanomaterials like carbon nanotube is difficult because so they tend to clump together. So the usage of this nanomaterials, the production of UHPC seems to be is a area where we can just look into it and see how the research can be done. Next one, the optimization of the filler ratio is another key area where the fibers have to be optimized for the production of UHPC. Since UHPC is not done at a wider scale, it has the enhancement of this research can be done for the production of UHPC in the larger scale. And furthermore, the research can be done to reduce the cost of the production of UHPC. The production of UHPC has to be broadened so that it can be widely used in all applications. So the sensing system of UHPC should be improved by usage of fibers with sensing capacity. So the functional and the mechanical properties can be further improvised with the optimum mixes and the production system. Is a future directions where we can work on this UHPC. So if you see in India, the notable projects are the bridge which is constructed in Mumbai in Telangana, and another one is the Mumbai-Nagpur Highway Express. So it is on 107 kilometer expressway, which features over 100 bridges. That has utilized this UHP for the connections. So another one is a bridge in Telangana, which is a major bridge which is built entirely with a precast segmental element. So it is on 1.2 kilometer long bridge constructed using the span by span method with precast segments. So if you see the future applications, so we have to see into the fully closed loop systems where sensing UHPC and the AA mode communicate models has to be developed for the real-time self-monitoring and the self-report with the human intervention. Next one is the optimization of the structures and the predictive models and the early warning of the structures is the future applications where this UHPC has to be developed. Next is the sustainability. The effective utilization of the available resources and the efficiency, which uses the materials on the life cycle management and also the safety aspects. This UHPC has to be used for this safety. So if you see the roadmap for this future research, so more focus has to be done on this UHPC towards sustainability, standardization, and smart functionality. So this integration of AI, 3D printing, and the green materials has to be furthermore developed. And also this generation of the codes or the development of the specific design procedures on the code provisions has to be developed for this UHPC. So if you see, if you're doing a short-term research, you can just work on this low-carbon UHPC mixes. the global available you can develop UHPC with the supplementary cementing materials such as GGBS, fly ash, and the rice ash gas. And also, you can just work on this life cycle assessment of this UHPC structures, and also the establish the regional laboratories and the testing protocols for this UHPC. If for a long-term research of for a medium-term research of about 3 to 7 years, we can uh, we can work on this development of the design standards and the codes, and we can also involve in developing training and the upskilling the contractors and the subcontractors and the engineers to work on this UHPC. And also this optimization of the fibers, mixing fibers and the curing techniques can be is another project, is a area where we can work for this fiber dispersion and the curing techniques. And also the pilot scale projects for the bridges and the precast system can be conducted. So the long-term research of for more than 7 years, you can work on this AI-assisted mix design, the development of this AI-assisted mix design, 3D printing techniques, and the application of UHPC in the extreme environmental conditions can be another area where we can work for, where the research can be done for the longer time. Next one, development of this utilization of this effective utilization of this eco-friendly materials and the carbon neural net additives, which is self-sensing, is another area where we can work. And the bio-based fibers such as hemp, sisal, and the flax. Not only hemp, sisal, and flax, we can go with another different materials for the production of this UHPC. And the recycled aggregates can be also used for this production of this. More focus can be done on this usage of this UHPC for the recycled aggregates for the production of UHPC. So if you see, more than 200 bridges products has been used in North America, and also in Asia, China, and Japan. Also, there is a rapid growth or the usage of this UHPC. So in India also there is a lot of projects has been done with this UHPC. To summarize, UHPC is a concrete with no coarse aggregate. So it is a concrete which is mainly made up of cement, fine aggregate, and the supplementary cementing materials, retarders, and the accelerators, and the super plasticizers are used to improve the workability. So it's a low water content concrete which mainly uses the steel fibers. So the steel fibers can be replaced with this biofibers. So this is the area where we can work. So it has a compressive strength greater than 150 megapascal and a post cracking strength of 20 megapascal, and it has an excellent durability. So coming to the workability, it is a self-consolidating concrete which possesses, which doesn't need any vibration. It is mainly used in the congested reinforcement or the heavy structures. In case of a bridge structures where there is a connections, heavy reinforcement will be there. In such cases, achieving the strength with a normal conventional concrete is quite difficult. So you can use this UHPC, which can act as which will provide the necessary strength. So if you see, it's mainly used in this bridge panel system, or it can be used. It is used as an overlay of deck, or it is used in the repair system, or it can be used to strengthen the existing structures. So mainly the bridges are constructed using this ultra high performance concrete, and the precast elements are also used. So if you see the usage of this UHPC reduces the use of use of the cement, steel, which provides a sustainable solution. So these are the emerging techniques or the emerging areas where this emerging areas in UHPC performance, that is ultra high performance concrete. So AI optimized and self-sensing UHPC, 3D printing, and the bio-based and the circular economy UHPC. We can also work on this enhanced fire resistant and the multifunctional UHPC. The another area is the ultra ductile and the seismic resistant UHPC. So concluding, so this UHPC. So if you see the evolution of UHPC, so we are moving from this high strength concrete to this high intelligent concrete. Production of this. So so UHPC is becoming a smart sensing material that does not only carry load, but monitors its own health and interacts with its environment. So next transition is from the laboratory material to the mainstream practice. So it becomes a go-to solutions for the resilient and the sustainable construction worldwide, from the lab to the normal practice. So from considering the durability aspects, so it is not no longer just about lasting a longer time, but also about doing so, which is adaptable for the future challenges. So as to conclude, the UHPC, it's a technology which is building the future of the infrastructure. So these are the references I've taken. So thank you all for listening. So it's quite a lengthy topic, and it is discussed more details. So although I have discussed few topics I have discussed here and there. So it's a very big topic, and it's a very big, wide area where we can do a lot of research on this ultra high performance concrete. So thank you all.
Thank you, ma'am. Participants, if you have any queries or doubts, you can clarify with ma'am. So I repeat, participants, if you have any queries or doubts, if you want to ask, you can unmute your mic and you can ask.
I can ask a question regarding this. Hello.
Yes, sir.
Hello. Can you hear me? Hello.
Yes, sir. Yes, sir.
Yeah. So regarding this high performance concrete, can it be used for mass concreting? Because my concern is that during mass concreting, there's a high release of heat,
Yes, sir.
and
Yes, sir.
since so this concrete shall be having a very high cement content probably.
Yes, sir. But if you see the researchers or the literatures of the work done, the UHSPC is not mainly carried out for this high mass concreting, like in dams and all these things. It's mainly the most wide use of this ultra high performance concrete is in the construction of the bridges. So it is mainly done in a controlled environment. A precast environment, or it's done as an overlay or to strengthen the structures. Like, it's not done for an heavy high that is mass concreting.
Mass concreting. Okay. Because my concern is what, because we as a consultant, we normally do projects in Middle East area where there's very high
Okay.
temperature, and if we
Okay.
propose such kind of concrete in roads or buildings, so is there any paperwork on this that we can reduce the temperature of this concrete while using this in projects like buildings
No,
or
no, sir. I
or
have
road work?
and Okay. So if you
Interesting program.
see this
Because
mass concreting, none of the literatures, yeah, to my uh, knowledge, I have not seen any research with this mass concreting of this mass concreting, the application of UHPC in this
concreting,
mass
but
concreting.
yeah, but
Yeah.
application of USC will give very high heat coefficient. Na? So I want that. Is there any paperwork
So
which says
yeah.
that it
So
can be reduced?
and also yes, sir. So if you see the conventional concrete, the amount of heat liberated will be more in case of a conventional concrete. Whereas in case of a UHPC, the usage of cement is less. So uh, coming to this heat liberation of heat, to my knowledge, it will be quite lower than that of a conventional concrete. So because of this high particle packing density, the strength
Okay,
is
very
mainly
good.
achieved because of this high particle packing density.
Okay, okay, okay. You mean to say due to the high fineness of the material, you get
Yes, sir. We have to do a
of
proper
the
mix
impact
design such that the
high
yeah,
tension.
we have to do proper mix design
Okay,
such that the particles are densely packed, which gives the compressive strength. This is not the hydration or the um, which in case of a normal concrete, a conventional concrete, the hydration process which gives the strength. Here, the UHPC, which it is the particle packing uh,
yeah.
density, which gives the high compressive strength.
And like, what is the lowest to least water to cement ratio that can be used in this type of concrete?
Yes, sir. Yeah, the water cement
What
ratio is. Uh, yes, sir. I'm not audible. Your voice is breaking. Can you just type it in the chat box? So the
lowest
water cement
minimum
ratio adopted is,
minimum which can be achieved?
yeah, the water cement ratio normally adopted, it should be less than 0.25.
Okay, okay, fine. Thank you, ma'am.
Yes,
Thank you.
thank you. Yes, sir. I'll definitely share the PPT for the reference. Sir, any other doubt?
So, any other participants, you have any clarification doubts?